In chapter 9, we're going to be dealing with probability. The first section we're going to look at is just the basics that are related, the basic things that are related to probability. And then the second section will deal with things like mutually exclusive events, dependent and independent events, and rules for handling events that include the word and the word or. Also, we use a tree diagram. I'll show you how to use a tree diagram for multi-stage experiments, and then discusses expected value, standard deviation, normal distribution, and odds. That would be section 9.3. All right, this first section is the basics of probability. Okay, that's section 9.1. Now we're going to talk about the qualitative phrases in probability. We did talk about that word qualitative, which is another way of saying categorical data in statistics. There are phrases that are qualitative in nature that deal with probability. Okay. Words and phrases such as impossible, unlikely, likely, and certain to occur are what we call qualitative phrases used in probability. And of course, probability is the chance that a certain event will happen. Okay. So you're going to be seeing these words or phrases in this particular concept of probability. All right, like in this case, it decide whether the situation is impossible, unlikely, likely, or certain to occur. Like in this case, you will win the lottery. Would that be impossible or unlikely or likely or certain to occur? That'd be unlikely because the probability of anybody winning the lottery, that's real low.
But it does exist.
Yeah, it does exist, but it's just, you know, it's real low. And we're going to be talking about things about the lottery and its probability in this chapter. Your pet will learn how to build a spaceship. That's impossible. Okay. And you will stay awake during the lecture, and I hope you do here.
Mhm.
Likely. Okay. Just hope you do here, because I know it's in the late afternoon, and some of us want to be done for the day. Okay. All right. And this is just something that deals with what elementary school students should know. So they'll be looking at activities such as flipping a coin, spinning a spinner, or drawing marbles from a bag. And those are just some activities that are used in probability. Like in this one, a teacher shows his class a bag containing 3 blue marbles, 15 red marbles, and 72 green marbles. The teacher randomly selects a marble from the bag. Use the word impossible, unlikely, likely, or certain to describe how likely it is that the teacher will draw a blue marble. Okay. Let's see. This case is unlikely because there's only 3 blue marbles in this bag, along with the 15 red and 72 green. What about a red marble? Again, that would be unlikely because there's 15 red marbles there. What about a green? Likely. Because there's 72 green marbles in the bag. Okay. And these are just the answers to that. And their reason. Few blue marbles there, so it's unlikely. Less than half the marbles are red, so that would be unlikely. And more than half the marbles are green, so that would be likely. Okay, so in this problem number 11, on page 504, in a bag of marbles, 1/4 are blue, 1/6 are green, 1/2 are yellow, and 1/12 are black. If you randomly draw one marble from that bag, which color is most likely? The yellow, because half of them are yellow. Because 1/2 in this case is more than 1/12, more than 1/4, and more than 1/6. So the answer there will be yellow. Questions on that particular problem? Okay. Let's talk about the language of probability. So here is the definition. An experiment is a procedure in which something happens, but the result is not known in advance. Okay. So an experiment can be things like tossing a coin, or rolling a fair die, or spinning a spinner with probably 8 numbers on it. Or it could be something like drawing a card from a deck of 52 playing cards. Now, an outcome is the result of an experiment. So if you toss a fair coin, it could be heads. Or if you roll a fair die, it could be, let's say, 5. That would be an outcome. Those would be outcomes from an experiment. Now, the next definition is sample space. That's the list of all possible outcomes from an experiment. So let's say rolling up their coin, they're, tossing up their coin, I should say. There are heads and there's tails. Those are all the possible outcomes. Rolling a fair die would be something like a 1, a 2. Well, yeah, rolling a fair die, 1, 2, 3, 4, 5, or 6. An event is a collection of outcomes. So an event could be things like rolling an even number on a fair die. All right, now by convention, the letter S, we represent that as the sample space. The other capital letters, A, B, and C, are represented by events. So like in this case right here, an experiment consists of spinning the 1 to 5 spinner, as you see here, and recording the number to which the arrow points to, okay? So if you were to look at this, the sample space would be all 5 numbers, 1, 2, 3, 4, and 5. And an event would be something like spinning an odd number. So in this case here, either getting a 1 or 3 or 5, because those are odd numbers. So on the next slide is pretty much what I got through talking about. The sample space is all 5 numbers, 1, 2, 3, 4, and 5. Event A, which is equal to 1, that's the event in which the spinner lands on a 1. And event B, where you have 1 and 2 there, that's the event where the spinner lands on either a 1 or a 2. Okay. And I did mention that spinning an odd number is an event, because it could be 1, 3, or 5. Okay, capital A is an example of a simple event because it consists of exactly one outcome. Okay, spinner landing on one, that's only one outcome. B is an example of a compound event. It consists of more than one outcome, either spinning a 1 or 2 in this case. That's considered to be a compound event. Okay. All right, questions on this? Okay, now in the next slide is example 4. Refer to the 1 to 5 spinner below, and then consider events A equaling to 2 and 4, and B equaling to 1 and 4. And in part A, we want to answer this question. If the spinner points to 3, did event A occur? Now, A only has the 2 and the 4. So if we spin a 3, that means that event A did not occur. Okay. And in part B, if the spinner points to 1, did event B occur? Yes, it did, because event B is spinning a 1 or a 4, and we end up getting a 1. So event B did occur. Okay. And these are just the solutions to that we just got through talking about. Okay. All right, next we'll look at using numbers from 0 to 1 to represent probability. Yeah, or percentages. Here's the expression P with the E in parentheses. That represents the probability or the likelihood or the chance that event E will occur. And you can quantify probability with either a fraction or percent or a decimal number. Okay. Now here's some things you need to know about probability. One of them will be an impossible event. That's where the probability of event E is equal to 0. Okay. So if I only had, let's say, red, orange, and yellow candies in a bag, and I want the probability of selecting a blue candy, that's an impossible event. Because there wouldn't be any blue candies in that bag when there's only red, yellow, and orange. And if event E is certain to occur, then that means that the chance of event E will be 1. So that would be a certain event when the probability of event E is 1.
Same thing if event E was orange, red, yellow,
Orange or red or yellow.
then you have to draw one of those out of the
Yeah.
bag. That's always in the bag.
Yeah. Mm-hmm. Any other questions? Okay. And we're going to be talking about combined probabilities shortly in this chapter. All right. Now, if we're uncertain that event E will occur, then that means that the probability of event E will be between 0 and 1. And this does include 0 and 1. Okay. So keep in mind, probabilities, I might as well say this, probabilities can be negative and probabilities cannot be bigger than 1. It's got to be between 0 and 1, including 0 and 1. And the closer your probability value is to 0, the less likely that event will occur. And the closer you are to 1 for the probability of that event, then it's more likely that the particular event will occur. Okay, so here is the concept map relating those qualitative phrases with the quantities from 0 to 1. At 0 is an impossible event, and at 1 is a certain event. Okay. If your probability is closer to 0, then it's very unlikely. Or if your probability is getting closer and closer to 1, it's going to be very likely. Okay. Unlikely would be less than half. Likely would be greater than half, 1/2. All right, questions on this? Okay. Now let's look at the experimental probability. Experimental probability. Let's say we observe that event E occurs F times when you repeat an experiment N times. Let's say you tossed up a coin, let's say 10 times, or 20 times, or 50 times. Okay, that would be an experimental probability here, that event E will occur. That'd be that fraction, F divided by N. And I don't know why this slide did not explain what F over N means. The F represents the number of times that the event happened, and the N is going to be the number of outcomes. I mean, not outcomes, the number of the frequency, I should say. Okay, like in this example here. An experiment consisting of rolling 2 standard die and then multiplying the numbers shown at the top of each die. So like if one die shows a 4 and the other one shows a 2, then you multiply 4 times 2 to get 8. Okay. So in part A, they want this. What is the experimental probability of getting a 3 or a multiple of 5? And in part B, it says, suppose you repeat this experiment 60 times based on the experimental probability in part A. How often would you expect to get a 3 or a multiple of 5? Okay. All right, so here, this is the event of getting a 3 or a multiple of 5. Okay, because think of this, if you roll a dice and the 2 numbers come up and then you multiply those 2, and it might help for me to do a table of all the possible outcomes here. So that way you can see where they're getting this. Okay, let me stop sharing this one and do this on the board. Let's say this first die, all the possible outcomes are here, 1 to 6. And on the second die, 1 through 6. And of course, we're multiplying these 2 together. So here, if I do 1 times 1, that'd be 1. 1 times 2 is 2. And then do 2 times each number. 2 times 1 would be 2, then 2 times 2 is 4, and so on. And then 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, and 3 times 6, and then 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5, 4 times 6, and then 5 times 1. 6 times 1. So these are all the possible outcomes when you roll 2 die and then you multiply the numbers that you came up with. Okay. So getting a 3 or a multiple of 5, well, then we can get a 3 here. A multiple of 5 would be something like this. 5 is a multiple of 5. 10 is a multiple of 5. It's 15, and then 20, 25, and 30 going this way. And these are the multiples of 5 going that way. And the other 3, I should say. Yeah. So the event of getting a 3 or a multiple of 5 would be 3, 5, 10, 15, 20, 25, and 30. Here, in that problem, they're listing those numbers only once, because they're not listing the 3 twice. No. Yeah, because that's 5, 6, 7, I mean 6, 7, 8, 9, 2. The probability of that would be 13 out of 36. Now, if we roll the dice 32 times, the actual outcomes were this. Okay, that's if you were actually doing this. So here, this is the frequency table that they have right here. The number of times that event E occurred, in this case, was 10 times. Because if you count up the number of times you roll a 3 or a 5, or a multiple of 5, it happened 10 times. The number of times that event E did not occur was, in this case, 22 times. Okay. So here, the frequency that we got a 3 or a 5 was 10, and then the number of times N, that was 32. So the experimental probability of getting a 3 or a multiple of 5 would be 10 over 32, which is approximately 31%. Okay. And those numbers that they came up with is just an example of what they did when they tossed the coin, in this case 32 times, and came up with those results. And now part B, based on the results in part A, we expect event E will occur 10 times out of every 32 rolls. That's basically what that means. Which leads us to a proportion. Because if we're going to roll the dice 60 times, okay, and we want to find out what that probability would be, or how often would you expect to get a roll of 3 or a multiple of 5? So here's the proportion: 10 over 32 equaling to A divided by 60. A is the number of times that we expected event E to occur when we roll the dice 60 times. And of course here, if we did the cross multiplication here, this is 32 times A, which is where that 32A comes from. That's equal to 10 times 60. That's this part right here. And then to solve for A, you divide both sides by 32 to get A by itself. So it'll be 10 times 60 divided by 32, which is exactly 18.75 or approximately 19. Okay, so based on that experiment, we could expect to get 19 rows. We would expect to get a 3 or a multiple of 5 19 times when the dice is rolled 60 times. Question?
So if we do mathematical probability, it comes up to 36%.
Yeah.
It's talking about experimental
It's
probability as being able to read a data set and project from that.
Yeah, because
Specifically.
see, this is what happened. They rolled the dice 32 times and came up with these outcomes right here.
Would that be proof that the dice are not fair considering they don't conform to the mathematical probability?
We can say that. Yeah, you can say that. Okay. Any other questions? Okay, take a look at problem number 3 on page 503. We're going to go over this one. A student repeated an experiment of randomly drawing one letter from a bag that contained 6 letters and recorded the frequency table shown. So there's the outcome for GRADES and the frequency for each letter. So here we want to find the experimental probability of each event. Okay, so let me okay, so G was 4, R is 5, and A is 1. D is 7, E is 3, and S is 5. And I'm going to find the experimental probability of each event, like in this one, of selecting an R out of the bag. And I'll go ahead and copy this one, E and A. Okay, so in this case here, we need to count how many, the total frequency here. How much is this? 25. Okay. So in other words, he drew letters out of the bag 25 times. And then let's see, the experimental probability of each event. Let's start with R. So here I want to find, let's say, the probability of pulling an R out of the bag. So I'm gonna write it like this. P with the R in parentheses, the probability of pulling an R out of the bag. So in this case here, how many R's are there in the bag? There are 5 out of the total number of letters in the bag, there are 25.
Does it change if you replace it afterwards?
Huh?
Does it change if you replaces it? We don't know that there's 5 in the bag, just that he drew it 5 times.
Well, let's just say that he just, randomly just selecting one letter out of the bag. Okay, we haven't gotten yet to, with replacement and without replacement yet.
Sorry.
I know you're ahead.
Sorry.
It's okay. All right. So here 5 out of 25 if we were to reduce that, this would be 1/5. Now, if they ask for the percent, you'll do 1 divided by 5 times 100. It'd be 20%. So in this case here, it will be a 20% chance that this student would select an R out of the bag containing 6 letters. Now, for part B, we got E and A. What that means here is this: the probability of selecting an E or an A. And basically what this means here is this: we just add the 2 probabilities here. The probability of pulling an E out of the bag and adding to it the probability of getting an A out of the bag. All right, how many times the E was selected? Well, what's the frequency for the E? 3 out of 25. And what's the frequency for pulling an A? 1 out of 25. So we just basically add the 2 probabilities together. What's 3/25 plus 1/25? 4/25. And it's already in simplest form. But let's say they want this as a percent. It'd be 16%. You do 4 divided by 25, that would give you 0.16, but here we multiply by 100 and add the percents on it. So it'd be 16%, meaning it'd be a 16% chance of this student selecting an A using an experimental probability. All right, any questions about problem number 3? Okay. All right, problem number 4. Number 6 on page 504. A bag has B blue marbles, Y yellow marbles, and G green marbles. There are N marbles altogether. An experiment consists of randomly drawing a marble from the bag. What does each fraction represent? Okay. So now we're given those fractions and we want to know in words, what does this mean based on this particular situation? Okay. All right, so let's think of this. B blue marbles, Y yellow marbles, and G green marbles. So, and N is the total number of marbles altogether. So, that Y over N means this: the number of yellow marbles out of the total number of marbles in the bag. This represents the probability of selecting a yellow marble. Okay, that's basically what they were looking for in this case. Questions on part A. All right, now part B. G over N. What do you think G over N would mean? Let's see, probability of selecting what? The green. This G represents the green marble. And what do you think B plus G divided by N would represent? Let's see, blue or. Okay.
Or how many polls are gonna come out?
Mhm. Okay. All right, any questions about problem number 6, and how that's done? Okay. All right, we'll look at short-term and long-term behavior of experiments. All right, we'll start with this. It is likely the 1-2 spinner in figure 2 would land on 2, based on that particular drawing, as you can see here. Because notice that it's just only about 1/4 of the spinner is 1 and everything else is a 2. So that means we would expect the spinner to land on 2 in 75% of the spins. Okay. Now, on the next slide that you're going to see is this table that displays some experimental results generated by a computer, where N is the number of spins, F is the number of times the spinner lands on 2. And F divided by N is going to be the fraction of times the spinner lands on 2. And this is what it looks like. And this is the fractional part to the nearest 1,000. So like 25 spins, the frequency was 17. The fractional, they do F17 divided by 25 to get 0.680. And then if they spin 65 times, the frequency of getting a 2 was 54. 54 divided by 65 came out to be 0.831, and so on. That's just a sample data for that 1-2 spinner that I showed you. Okay. Now in this figure, of course, the fraction F over N would be always a number from 0 to 1. So this is the graph of the ordered pairs, N and F divided by N. N is the number of spins, the fraction of times that the spinner lands on 2, that's the vertical axis. And this is what they generated from a computer. And of course, it's always a number from 0 to 1. And if you notice that the more spins that you do, that probability would get closer and closer to 0.75 based on that spinner.
Can I ask, like logistically speaking, if you were to take a cross section of any of those pieces of spins, they should reflect all of them.
Well, it's just how the spinner is made. I can tell you that. Yeah. Because that 2, that represents 75% of the space. And the 1 is only 25% of the space there.
I'm just wondering why the variance early instead of all the way through.
I don't know. That's how they do it. Okay. Questions? All right. Small values of N represents the short-term behavior, and large values of N represent long-term behavior. So in that case, that graph that I just showed you fluctuates widely for small values. And I'll go back to that. See, for these small values right here between 0 and 500, they started fluctuating big time. And then when you get to large values, it hovers around that 0.75. So here's a table suggesting that the experimental results are unpredictable for low number of repetitions of an experiment, but more predictable for a large number of repetitions. So the more you do this, the more spins that you do, then what's going to happen here is it gets closer and closer to the probability of rolling a 2, which is theoretically 0.75 based on that the way that spinners created. Questions on that? All right, so for larger n, we will see the graph settle more closely to 0.75. So in this particular problem number 4 on page 504, we have data for Raj, Gina, and Taylor. Okay. I'm not sure. I'm not sure what they mean with the n in this case, but here's just something that they did. Let's say n times, and it occurred this many times out of a total of n. Okay, whatever event E is. So here for each student, we're going to determine the experimental probability that E occurred. And in part B, which experimental probability seems like the best estimate for the probability of E, and how could these results be combined in some way to obtain a potentially better estimate of the probability of E. Okay, so let's look at this problem. So I'm just writing times event E occurred. And the N here for Roger was 68 out of 120. For Gina, it was 147 out of 250. And then for Taylor, it's 260 out of 400. All right, and we want the experimental probability for each one. All right, so for Raj, the probability that event E occurred in his case, that's the number of times event E occurred over the frequency. Well, not frequency, the number of the total number of events they did. So this is going to be 68 over 120. And then for Gina, the probability, her probability that event E occurred, that's going to be 147 out of 250. And then finally for Taylor, the probability of event E occurring, that's just simply going to be 260 out of 400. Okay. And I believe that's all they're asking for here. Now, I'm not sure if they want this reduced in simplest form for your fractions. If they do ask for it in WebAssign, make sure that you simplify it. Okay, part B. Which experimental probability seems like the best estimate for the probability of E? So which one of these three would be the best estimate for the probability of event E?
Just the long-term results are more reliable, so or that could be the best test one.
Well, that's yeah. And it will be this number, this probability right here, 260 over 400. The reason why they say that because 260 over 400 is more than 1/2. Okay. It's more than 50%. Okay. And this is due to the large value of n. Or larger value of n.
All the percentages are 50%.
Well, oh, they are? Okay. Because this 1/2 over 1/2, that's over 1/2. But if you look at your n, yeah, that 400 would be better. Okay, so that probability 260 over 400 would be a better number, a better estimate for the probability of event E. And then part C was, how could these results be combined in some way to obtain a potentially better estimate for the probability of event E?
Average percentages.
I would add these up. Okay. So I would add the number of times that event E occurred for each one of these. So this numerator, I'm gonna say probability of event E. This will be the sum of the number of times event E occurred divided by the sum of these n values, 120, 250, and 400. And if you add 68, 147, and 260, you would get, I think, what, 475 divided by 120, 250, and 400. This will be 770. And someone do this. What's 475 divided by 770 times 100?
62%.
Okay, approximately 62%. Yeah. All right, any questions about problem number 4 on page 504? Okay. All right. Let's see, I guess we can stop right here with this particular problem. All right, and this is where I'll pick up next time. That's the law of large numbers and theoretical probability. Okay. Mhm. All right. Of course, go ahead and turn in your first hour class assignment. Just leave it at the front table. And if you've emailed it to me, that's fine. I'll check my email before I leave here and try to print those off. Monday, we will finish section 9.1.
Bakery open today and then quiz open
Yeah.
today.
Yes, yes. Mhm. Y'all have a good weekend.
All right.
You too, sir.
All right.